Hopefully now we're very familiar with rational numbers, and we're going to look at the irrational numbers. We have a shorthand way of expressing all the rational numbers, and that's with a Q, with a small little line, vertical line there, and the irrational numbers we'll use the capital letter I with two strokes. So that's just a shortcut way of writing down the rational and irrational numbers. So the rational numbers, if we think of all the rational numbers in our number system, are all the numbers that can be expressed as a ratio of two integers. So we'll have a numerator and a denominator. So if you can express a number with a numerator and denominator, it falls into the category of rational numbers. Now, if this is all the rational numbers, which, as I say, is represented by Q, then, if you like, we've got a subgrouping, or what we call a subset, which are all the integers. And don't forget, integers can be positive and negative, and we also include zero. So positive, negative, and also zero. So the integers, if you like, the number 6 can be just expressed as 6 over 1. So that's why it falls into the category of rational numbers. And we could also have, say, -2, which is also equal to -2 over 1. So still a ratio of two integers. So everything out here could be numbers like 1 over 8, 17 over 18, 2 1/4, minus 18 1/2. So they're outside there, and the integers are inside there. So that's our grouping, if you like. We're trying to get a bit of an understanding of how all our numbers in the number system fit together. The irrational numbers can't be expressed as the ratio of two integers. And there are lots of them. I'm going to just talk about a few of them here in detail, but there are a number of irrational numbers. If we go back to our number line, we've already seen that we've got our integers, then we've got our numbers that occur on the dots in between each of these, and they are our fractions. So now we're going to look at other numbers that occur on the number line that go in between the fractions even. So our irrational numbers, we use that symbol. Rational numbers, we use that symbol. Let's look at one, and that's first one is just the number pi, and pi is not exactly 3 1/7. It is approximately equal to 3 1/7, because you could say, well, okay, then if it was 3 1/7, it would be a rational number, but that's just an approximation. That's not the exact value of pi. Pi is simply, if you've got any circle, and this is the power of the discovery of pi, doesn't matter how big your circle is, if you could measure around the circumference and you could measure exactly the diameter, pi is simply the ratio of the circumference to the diameter. So that will allow us to use pi in many forms, or many applications, because from that we can get the circumference equals pi multiplied by the diameter. So given the diameter, we can work out the circumference. Given the circumference, we can work out what the diameter is. And once we know the diameter, obviously we know what the radius is. So that's an example. Another example, pi would sit out here somewhere. We know that it's 3.1415, etc. It just keeps on going. It's what we call a non-terminating decimal. It goes on indefinitely. There is no stopping to pi, and you may have seen, you can look on YouTube and see people who have memorized so many thousands of decimal places of pi. It's a great way to spend your time. Then the other thing, it has no repeating pattern. So if we look at this and go through, you can't. There is no pattern that is repeated as you go through all the decimal places of pi. And if you like, that's another way of looking at what an irrational number. It is a non-terminating decimal, and it has no and it has no repeating pattern, because just a non-terminating decimal is not enough. For instance, the number 1/9 is equal to 0.111111. So, and so on. So 1/9 is a non-terminating decimal, but it has a repeating pattern, so it falls into the category of a rational number. Once again, the ratio of two integers. So that is the number pi. Another number that we can look at, another irrational number, is the number e. Now e is the exponential number. It was given the name E after Euler, who was a famous mathematician, and E is actually is something that has just been able to fit quite well when we're trying to describe natural growth or natural decay. By that I mean, if you've got a population and you want to try and come up with some sort of mathematical model for the population and how it grows over time, the number E can be used in that model quite effectively to be able to do predictions. It's the same with radioactive decay. E also is used to model the decay of substances over time. So E is a number that you are going to get used to and going to be used extensively in this course. It is approximately equal to, and we use wavy, just like we got up here. Pi is approximately equal to 3.14159. E is equal to 2.7182, etc. That number, once again, can be put on a number line up here somewhere. Fills in the gap. A formula for E is 1 plus 1 on n, all raised to the power of n, where n is very large. The larger you make n, the closer the approximation to E is. So on your calculator you could put 1 plus 1 over a million, all raised to the power of a million. That will be a good approximation. If you made it 10 million, it'd even be closer, and so on. We say n approaches infinity. So as n gets larger, this gets closer to the value of E. So there's just two irrational numbers we're going to talk about more in the future. The numbers pi and E, they can't be expressed as the ratio of two integers. They are non-terminating decimals that don't repeat in pattern. So that puts everything a little bit better into some sort of shape, and we'll explore that in the future.